Okay, let's look at one more example here where we're going to do a triple integral, and this is another one that works really well with spherical coordinates. So it's a volume integral. Find the volume of this region. So I'm going to set that up as a triple integral. So volume is triple integral over the region D of just dv, or 1 dv if you want to write the 1 there. All right, so let's sketch this region and talk a little bit about why we would know that spherical coordinates would work well here. So we want the region that is above the xy plane. Okay, so I don't need to sketch the xy plane. I just know we want the part of whatever is above the xy plane. Below the cone, z equals square root of x squared plus y squared. So that cone is the cone that goes up the z-axis, opens up the z-axis, circular cone. We've seen that several times in several of the problems we've worked on. Just the top half of that cone. And then inside this sphere of radius 2, centered at the origin. All right, so let me just attempt to kind of draw at least the top part of the sphere. I don't need the whole sphere here because we are really interested in only the part that is above the xy plane. Okay, so we want the region that is above the xy plane, below that cone, and inside that sphere. So if I think about the region that is below the cone, there's the edge of the cone and where that cone meets the sphere. So below the cone would be this part here, below the cone, and then inside the sphere. So inside the sphere, if I kind of darken the edges of the sphere here. All right, so the sphere is going to be on the outside. I wouldn't actually be able to see the cone if I look at it from the outside, but it's like there would be this little hole in the middle. I guess I would be able to see maybe the back edge of where that cone is. So there's this sort of hole in the middle, a dip, like a little volcano or a pit in the top of this surface here. So the cone dips down on the inside. All right, so that is the region we're interested in finding the volume of, so that's how we want to set up our integral. How we would know that this works really well with spherical coordinates is that all of the surfaces that make up the edges of that solid are things that are constants in spherical coordinates. All right, so when I think about that region, if I think about going through that region in the direction of increasing phi, so I start on the positive z-axis and rotate downward. So when I start on the positive z-axis, notice that I'm in that hole that's in the middle there. I'm not actually on the surface. And when I first enter the actual surface is when I hit the side of that cone. So that's that cone that makes angles that are 45 degrees with the coordinate axes. So that would be phi equals pi over 4 is where I enter that, not only rotating down there, but in all directions. That's where I'm going to first enter that solid surface. And then I'm going to leave the surface when I hit that xy plane that's there. So that would be that I leave when phi equals pi over 2. All right, so the phi goes from the cone, phi equals pi over 4, to the plane, the xy plane, phi equals pi over 2. When I go through the region in the direction of increasing rho, I'm going to start at the origin. That's where rho equals 0. And then as I go through the region in the direction of increasing rho, I exit through the equation of the sphere. So that'll go from rho equals 0 to rho equals 2. And then the theta, I'm not going to label that here on the picture, but because we're going all the way around, there our theta will go from 0 to 2 pi. All right, so this is completely made up of surfaces that are constant in spherical coordinates. So this is just like integrating over a box in rectangular coordinates. This would be the kind of the equivalent in spherical coordinates. So our limits of integration are all going to be constant. All I need to do is remember how to convert my dv to spherical coordinates. So hopefully you have that memorized. Rho squared sine phi, d rho, d phi, d theta, in whatever order you want to do those in. I'm just going to do them in that order. All right, so our integral, I'm going to do theta on the outer integral. That will go 0 to 2 pi. And then phi on the next inner integral. So from our picture there, we see that that phi goes from pi over 4 to pi over 2. And then rho goes from 0 to 2. And then here, the function that I'm integrating is really just 1, so I don't really need to convert that to spherical coordinates. That's just a constant. And then as part of the dv, I have the rho squared sine phi, and then a d rho, d phi, d theta. And you could really do those in any order. Okay, so the integration on this one's pretty straightforward, a lot easier than the last problem we looked at. So let's go ahead and do that. Okay, so after I integrate with respect to rho, when I integrate rho squared, I get 1/3 rho cubed, and then I plug in my limits of integration. I let rho go from 0 to 2, so I get 8/3 sine phi, and then I'll integrate with respect to phi. Okay, so be careful when you integrate that sine function with respect to phi. Remember, you're going to get that negative right out front there. So the integral of sine is negative cosine. And then I'm going to plug in my limits of integration. Let me scroll up and do that. Okay, so when I plug that in, make sure you're careful about the order there, not just letting things go away. But cosine of pi over 2 is 0. So I'm just going to be left with this last part here that I need to simplify. Okay, so I just have this constant, which I can simplify, and then when I integrate with respect to theta, I'll have 4 square root of 2 over 3 times theta evaluated from 0 to 2 pi. So 4 square root of 2 over 3 times 2 pi, or 8 square root of 2 pi over 3. All right, so that's that volume of that region that we started with at the beginning.